we begin our journey at the only place in the universe that we truly know with certainty, Earth. At first glance, Earth feels enormous. It is filled with vast oceans that stretch farther than the eye can see, mountain ranges that rise like giants from the surface, and endless deserts, forests, and ice fields that give the impression of a world without limits. From where we stand, everything around us feels absolute. The ground beneath our feet feels stable and permanent, and the sky above feels like a ceiling that holds everything in place. Human life is built entirely within this narrow band of experience, and because of that, our sense of scale is shaped by what we can touch, see, and walk across. Yet, as we begin to step back mentally and look at Earth from a broader perspective, everything we think we understand about size and distance starts to change. On a human scale, the distances we travel every day already feel significant. Walking across a city, driving between towns, or flying across countries all seem like major journeys. A few hundred kilometers can feel like crossing a large portion of the world. But when we shift our thinking beyond human experience, these distances begin to shrink into something far smaller than we ever imagined. Earth, despite its vastness to us, is only about 12,742 kilometers in diameter. It is a sphere floating in space, held together by gravity, rotating once every 24 hours, giving us the cycle of day and night that shapes every aspect of life. From the surface, we do not feel this motion, yet the entire planet is constantly spinning through the emptiness of space at incredible speed. If we imagine stepping away from Earth, rising higher and higher until we can see the entire planet from above, something remarkable happens. The world that once felt infinite begins to look like a single object suspended in darkness. The continents, which once seemed so large and separate, now appear connected as part of one unified sphere. Oceans wrap around land masses like a thin layer of blue glass. Weather systems swirl across the atmosphere in slow motion, forming beautiful spiral patterns that move silently across the planet. From this distance, there are no borders, no cities, no individual landmarks that define human existence. Everything that we consider familiar becomes part of one small world. As we continue to move farther away, even this entire planet begins to shrink. Earth becomes just one object among many in a much larger environment. It orbits the Sun at an average distance of about 150 million kilometers, a scale so large that it is difficult to truly comprehend. This distance is called an astronomical unit, and it becomes the first step in understanding how enormous space truly is. At this scale, Earth is no longer the center of anything. It is simply one planet among others, following a fixed path around a star that is far larger and more powerful than anything on the surface of our world. From this perspective, Earth starts to lose its dominance in the story of the universe. It is still our home, still the only place where life is known to exist, but it is no longer unique in its role as a celestial object. It is one of many planets in a system that contains a wide variety of worlds. Some are rocky like Earth, others are gas giants many times larger, and some are barren, frozen, or scorched by heat. Each planet follows its own path, yet all are held together by the gravitational pull of a single star. As we continue to expand our view, we begin to understand the Sun, the object that defines our entire system. The Sun is not just a large light in the sky. It is a massive sphere of hot plasma, so large that more than 1 million Earths could fit inside it. Its gravity is what holds the solar system together, keeping all the planets in their orbits. Without it, the structure of our planetary system would collapse into chaos. The Sun is the source of nearly all energy on Earth, directly or indirectly. Every ray of sunlight that reaches our planet has traveled for about 8 minutes across space before arriving at our atmosphere. That means when we see the Sun, we are always seeing it as it was 8 minutes ago, not as it is in the present moment. This idea alone begins to change our understanding of reality. It means that even light takes time to travel, and the universe is so large that what we see is always slightly in the past. The closer something is to us, the less noticeable this delay becomes. But as distances increase, this delay becomes more significant. The Sun is just the beginning of this realization. Beyond Earth and the Sun lies the rest of the solar system, a vast region of space that extends far beyond the outermost planet. The solar system is not just a collection of planets, but a complex structure filled with moons, asteroids, comets, and invisible forces. The planets orbit the Sun in nearly circular paths, but these orbits are separated by enormous distances. Mercury, the closest planet to the Sun, moves through intense heat and radiation. Venus, often called Earth's twin, is wrapped in thick clouds of toxic gas and extreme pressure. Mars, the red planet, carries the remnants of ancient rivers and valleys, hinting at a time when it may have had a very different environment. As we move farther out, we encounter the gas giants, massive worlds made mostly of hydrogen and helium. Jupiter, the largest planet in the solar system, is so large that it could fit all other planets inside it many times over. Its great red spot is a storm larger than Earth itself, raging for centuries without stopping. Saturn, with its iconic rings made of ice and rock, presents one of the most beautiful sights in the solar system. These rings stretch across hundreds of thousands of kilometers, yet they are incredibly thin compared to their width, showing how delicate even massive structures in space can be. Beyond Saturn lie Uranus and Neptune, the ice giants, cold and distant worlds that receive very little sunlight. Their blue colors come from gases in their atmospheres, and their extreme distances from the Sun mean that sunlight there is extremely weak compared to what we experience on Earth. At this point, the solar system begins to fade into darkness, and the influence of the Sun slowly weakens as we move farther away. But the solar system does not end with the last planet. Beyond Neptune lies a region filled with icy objects, comets, and distant bodies that form the outer edges of our system. Even farther out is a vast spherical shell of debris known as the Oort cloud, a region so distant that it is difficult to confirm its exact boundaries. This is where the Sun's influence becomes extremely weak, yet still present enough to hold these distant objects in orbit. When we reach this outer boundary, we are still only at the edge of our own cosmic neighborhood. Beyond it lies interstellar space, the space between stars. This is where the true scale of the universe begins to reveal itself in a dramatic way. The distances here are no longer measured in millions of kilometers, but in light years. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. Even the nearest star to the Sun, Proxima Centauri, is more than 4 light years away. This means that even traveling at the speed of light, it would take over 4 years to reach it. At this point, human intuition completely breaks down. The distances are too large to imagine in everyday terms. The solar system, which once seemed vast, now appears as a tiny island in a much larger ocean of space. Between stars there is mostly empty space, but even this emptiness is not truly empty. It contains thin gas, dust, and cosmic particles spread across enormous distances. As we continue to expand our view, we begin to see that stars are not isolated. They are part of a much larger structure known as a galaxy. Our Sun is just one of hundreds of billions of stars that make up the Milky Way galaxy. The Milky Way is a massive spiral system, about 100,000 light-years across, containing vast clouds of gas, dust, and star clusters. It is so large that light takes 100,000 years to travel from one side to the other. Within this galaxy, our solar system is located in a relatively quiet region, far from the chaotic center where a supermassive black hole resides. From this perspective, our Sun is just one ordinary star among billions of others, each potentially hosting its own system of planets. The idea that Earth is unique begins to fade even further as we realize how many stars exist, each with its own history and structure. And yet, even the Milky Way is not alone. It is part of a local group of galaxies, each separated by enormous distances. Nearby galaxies like Andromeda are even larger than our own, containing trillions of stars. These galaxies move through space, sometimes interacting, sometimes colliding over billions of years, slowly reshaping the structure of the universe. At this stage of understanding, Earth is no longer even a small part of the picture. It is almost invisible on the cosmic scale. A tiny planet orbiting an ordinary star, in one galaxy among billions, in a universe that stretches far beyond what we can observe. The scale becomes almost incomprehensible, yet it is real and measurable. And still, this is only the beginning of the journey. As we leave Earth behind and travel farther into space, the first destination that truly changes our perspective is the Moon. It is the closest celestial body to our planet, yet even this closest neighbor is separated from us by an average distance of about 384,400 kilometers. On human terms, this distance feels unimaginable. It is far beyond any journey we make in daily life, far beyond continents, oceans, and atmospheric flight paths. Yet in cosmic terms, the Moon is still right next door. This contrast between human intuition and cosmic reality is the first moment where scale begins to break our natural understanding. When we look at the Moon from Earth, it appears small, almost fragile, hanging quietly in the night sky. It changes shape throughout the month, shifting through phases as it orbits our planet. These phases have guided human timekeeping for thousands of years. Entire civilizations have tracked agriculture, rituals, and calendars using the Moon's cycle. But what appears to be a delicate light in the sky is actually a massive rocky world, about 1/4 the diameter of Earth. Its surface is covered in dust, craters, and ancient scars from billions of years of impact. There is no atmosphere to soften the sunlight, no weather to erode the landscape, and no sound to travel across its surface. It is a silent, frozen world that has remained largely unchanged for eons. Standing on the Moon would feel completely alien compared to Earth. Gravity is only about 1/6 of what we experience on our planet, meaning a human could leap several meters into the air with little effort. The sky would always appear black, even during the daytime, because there is no atmosphere to scatter sunlight. Earth itself would hang in the sky like a glowing sphere, slowly rotating, showing clouds, oceans, and continents from a distance. From the Moon, Earth becomes the dominant object in the sky, not the other way around. This reversal of perspective is one of the first emotional shifts in understanding cosmic scale. What we think of as home becomes a distant object, and what we think of as nearby space becomes a vast, silent emptiness. As we move beyond the Earth-Moon system, we begin to understand that this relationship is only a small part of a much larger structure. The Moon is not alone in orbiting planets across the universe. Many other planets in the solar system have moons of their own, some even larger than our Moon. Jupiter alone has dozens of moons, each with its own unique characteristics. Some are icy, some are volcanic, and some may contain subsurface oceans hidden beneath thick layers of ice. These moons hint that even small celestial bodies can hold complexity and mystery beyond what we expect. But the true importance of the Moon is not just its physical presence. It is also a stepping stone in our journey outward. It is the first place beyond Earth that humans have physically reached. When astronauts traveled to the Moon during the Apollo missions, they did not just land on another surface. They crossed a boundary that had existed since the beginning of human existence. For the first time, humanity looked back at Earth from another world. That moment changed the way we see ourselves forever. Earth was no longer the entire stage of human existence. It became one object among many in space. From the Moon, the next step outward takes us into the broader structure of the solar system. The distances begin to increase dramatically. The space between planets is not empty in the way we often imagine. It is filled with solar, wind, magnetic fields, dust particles, and radiation streaming outward from the Sunday. Yet, compared to the size of planets and moons, this space is overwhelmingly empty. If the Earth and Moon feel far apart, then the distance to the next planet is on a completely different level. The inner solar system contains rocky worlds like Mercury, Venus, Earth, and Mars. These planets are relatively close together in cosmic terms, yet still separated by tens of millions of kilometers. Traveling between them is not a matter of days or weeks in any natural sense. Even spacecraft require months or years to reach their destinations using carefully calculated trajectories and gravitational assists. Mars, for example, can be anywhere from about 54 million kilometers to over 400 million kilometers away from Earth, depending on orbital positions. These variations alone show how dynamic and complex the solar system is. As we move outward, we reach the asteroid belt, a region filled with rocky fragments that never formed into a planet. These objects range from tiny dust grains to dwarf planets like Ceres. Contrary to popular imagination, the asteroid belt is not a dense field of dangerous rocks. Instead, it is mostly empty space with vast distances between individual objects. A spacecraft traveling through it would likely pass through without encountering anything at all. Yet, the total mass of this region still tells a story about the early formation of the solar system, when material was still gathering and organizing under gravity. Beyond the asteroid belt, the scale expands further into the realm of the gas giants. Jupiter dominates this region with its immense gravitational influence. It is so large that its gravity affects the entire solar system, subtly shaping the orbits of comets and asteroids. Its magnetic field is also the strongest of any planet, creating radiation zones that would be lethal to humans without protection. Saturn follows as a world of rings, a structure so vast that it stretches hundreds of thousands of kilometers, yet so thin that it would appear almost invisible if viewed from the side. As we continue outward, we encounter Uranus and Neptune, the ice giants, where sunlight is so weak that it takes hours or days for solar energy to reach them in usable amounts. At these distances, the sun appears no brighter than a very bright star in Earth's sky. The warmth and energy that define life on Earth are almost absent here. These planets mark the boundary of the classical solar system, but not its true edge. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies and dwarf planets. Objects like Pluto reside here, once considered the 9th planet of our solar system. The Kuiper Belt is a reminder that planetary classification is not always clear-cut. Instead, it is a continuum of objects ranging from small, icy rocks to large, spherical bodies. Even here, the Sun still exerts its gravitational influence, though it is extremely weak compared to its power near Earth. At this point, the concept of distance begins to shift again. We are no longer thinking in kilometers or even millions of kilometers. We begin to think in terms of astronomical units and light travel time. The Sun's light takes more than 4 hours to reach the outer edges of the Kuiper Belt. That means if the Sun were to suddenly disappear, it would take hours before the outer solar system even realized it. Beyond this region lies the Oort cloud, a theoretical shell of icy objects that surrounds the solar system at an immense distance. It is so far away that its existence is still inferred rather than directly observed. The outer edge of this cloud may extend nearly a light year from the Sunday. Here, the Sun's gravitational influence is extremely weak, and objects drift slowly through space, barely bound to our star. When we finally cross this boundary, we enter interstellar space. This is the true beginning of the space between stars. It is not empty in the absolute sense, but it is extremely sparse. A few hydrogen atoms per cubic centimeter, traces of dust and cosmic radiation fill this vast region. It is in this emptiness that the true scale of the galaxy begins to reveal itself. The nearest star system to our own, Proxima Centauri, is more than 4 light-years away. This means that even traveling at the speed of light, which is the fastest possible speed in the universe, it would take over 4 years to reach it. For any human spacecraft using current technology, the journey would take tens of thousands of years. This alone shows how deeply limited human travel is when compared to the scale of space. Between stars there is no familiar structure like planets or stable orbits in most regions. Instead, space is shaped by weak gravitational fields, magnetic turbulence, and the remnants of ancient stellar explosions. Supernovae, the explosive deaths of massive stars, spread heavy elements across space, seeding future star systems with the materials needed for planets and, eventually, life. In this way, even the emptiest regions of space are connected to cycles of creation and destruction. As we expand our view further, we begin to see that stars are not scattered randomly. They form groups, clusters, and eventually entire galaxies. Our Sun is just one star among hundreds of billions in the Milky Way galaxy. Each of these stars may have its own planetary system, its own history, and its own physical characteristics. Some are much larger and hotter than the Sun, while others are smaller and cooler. Some burn for only millions of years before dying, while others can shine for trillions of years. The Milky Way itself is a massive rotating structure, about 100,000 light-years across. It contains spiral arms filled with stars, gas clouds where new stars are born, and dark regions filled with dust that block visible light. At its center lies a supermassive black hole, an object with such strong gravity that not even light can escape it. Around this center, stars orbit in complex patterns influenced by the combined mass of the galaxy. From this perspective, our solar system is not just small, it is almost invisible. A single point in a vast rotating structure that itself is only one of many galaxies in the universe. And yet, despite this overwhelming scale, it is within systems like this that planets form, and within planets like Earth that conditions arise for life to exist. As we end this chapter, the moon, once a bright companion in our night sky, now feels like a gateway. It marks the first step beyond Earth, the first expansion of human perspective into the cosmos. From here, every increase in scale is not just a change in distance, but a change in understanding. Each layer of space reveals that what once felt enormous is only a fragment of something far greater, and that the true scale of the universe is only beginning to unfold. We now step deeper into the structure that surrounds our home, the solar system. At first glance, it may seem like a simple arrangement, a star at the center and a group of planets orbiting around it. But when we begin to examine it in detail, the solar system reveals itself as something far more complex, dynamic, and vast than anything we experience on Earth. It is not a static system. It is a living, moving environment shaped by gravity, time, and motion on scales that stretch far beyond human intuition. The solar system began its story about 4.6 billion years ago, long before Earth existed in its current form. It formed from a massive cloud of gas and dust known as a solar nebula. This cloud was not uniform. It contained regions of slightly higher density, and over time, gravity began to pull material together. As more and more matter gathered in the center, pressure and temperature increased, until nuclear fusion ignited. At that moment, the Sun was born. This event did not just create a star, it created the gravitational anchor that would shape everything around it. What remained of the original cloud flattened into a rotating disk. Within this disk, particles collided, stuck together, and gradually formed larger bodies. These became the planets, moons, asteroids, and comets that we see today. This process was not calm or orderly. It was violent, chaotic, and filled with collisions that reshaped entire worlds. Early Earth itself was struck by massive objects, including one that likely formed the Moon. The solar system we see today is the result of billions of years of gradual stabilization after this chaotic beginning. At the center of everything is the Sunday. It contains more than 99.8% of the total mass of the entire solar system. This fact alone changes how we think about our place in it. All planets, moons, asteroids, and comets combined make up only a tiny fraction of the system's total mass. The Sun is not just the center in a visual sense. It is the dominant force in every gravitational interaction within its reach. The Sun is a sphere of plasma undergoing nuclear fusion in its core. Hydrogen atoms are fused into helium, releasing enormous amounts of energy in the process. This energy travels outward from the core, slowly making its way to the surface before being released into space as sunlight. The journey of a single photon from the Sun's core to its surface can take thousands or even millions of years. But once it escapes, it travels across space in just over 8 minutes to reach Earth. This contrast between slow internal processes and fast external travel is one of the many hidden complexities of stellar physics. Surrounding the Sun are the planets, each with its own unique characteristics and history. Mercury, the closest planet, is a world of extremes. Its surface is scorched by sunlight during the day and frozen in darkness at night. With no significant atmosphere, there is nothing to regulate temperature or protect its surface. Venus, often called Earth's twin in size, is anything but Earth-like in conditions. Its thick atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system despite not being the closest to the Sunday. Earth, our home, sits in a narrow region known as the habitable zone. This is the distance from the Sun where temperatures allow liquid water to exist on the surface. This simple condition is one of the key requirements for life as we know it. Earth's atmosphere, magnetic field, and geological activity all work together to maintain a stable environment over long periods of time. Without the Sun's energy, this balance would not exist. Mars lies just beyond Earth, a cold and dry world that once had flowing water on its surface. Evidence suggests that rivers, lakes, and perhaps even oceans once existed there billions of years ago. Today, Mars is a desert planet with a thin atmosphere, but it remains one of the most studied worlds in the solar system because it may hold clues about past life or future human exploration. Beyond Mars lies the asteroid belt, a region filled with rocky remnants from the early solar system. These objects never formed into a planet due to the strong gravitational influence of Jupiter. Instead, they remain as scattered fragments, ranging in size from tiny dust particles to dwarf planets like Ceres. While often portrayed as a dangerous field of debris, the asteroid belt is actually mostly empty space. The distance between objects is so large that spacecraft can pass through it without risk of collision. Jupiter dominates the outer region of the inner solar system. It is a gas giant with a mass greater than all the other planets combined. Its great red spot is a storm system that has been raging for centuries, larger than Earth itself. Jupiter's strong gravity plays a major role in shaping the solar system. It can capture or redirect comets and asteroids, acting as both a shield and a disruptor depending on the circumstances. Saturn follows as one of the most visually striking planets. Its ring system is made of countless particles of ice and rock, each orbiting the planet like a miniature moon. These rings are incredibly wide, but extremely thin, showing how space structures can be both massive and delicate at the same time. Saturn itself is a gas giant like Jupiter, with a low density that is actually less than water. Uranus and Neptune are often called ice giants because of their composition. They are colder and more distant, receiving very little sunlight. Uranus rotates on its side, likely due to a massive collision early in its history. Neptune, the farthest known planet in the solar system, has strong winds that can reach speeds faster than any storm on Earth. These outer planets show that the solar system becomes increasingly strange and extreme as we move away from the Sunday. Beyond Neptune lies a vast region filled with icy bodies known as the Kuiper Belt. This region is home to dwarf planets like Pluto, as well as countless smaller objects. These icy remnants are thought to be leftover building blocks from the formation of the solar system. They are preserved in deep freeze, largely unchanged since their creation billions of years ago. Even farther out, the solar system extends into the Oort cloud, a theoretical region that surrounds the system like a distant shell. It is so far away that the Sun appears only as a bright star in the sky from there. Objects in the Oort cloud are loosely bound to the Sun, and their orbits can take thousands or even millions of years to complete. Some long-period comets originate from this region, falling inward toward the Sun after being disturbed by gravitational interactions. The space between these regions is not empty. It is filled with the solar wind, a continuous stream of charged particles flowing outward from the Sunday. This wind creates a protective bubble around the solar system known as the heliosphere. Within this bubble, the Sun's influence dominates. Beyond it lies interstellar space, where the influence of other stars begins to take over. To understand the scale of the solar system, it helps to consider distance in terms of light travel time. Sunlight takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. It takes more than a year to reach the outer edges of the heliosphere. These numbers show how quickly distances expand as we move outward. Human exploration of the solar system has been limited to robotic spacecraft. Missions like Voyager 1 and Voyager 2 have traveled farther than any human-made objects in history. Launched in 1977, they have spent decades traveling outward and have now entered interstellar space. Even at their incredible speeds, it took more than 35 years for them to reach the edge of the Sun's influence. This alone shows how immense the solar system truly is. Despite its size, the solar system is only a small part of a much larger structure. It exists within the Milky Way galaxy, which contains hundreds of billions of stars. Each of these stars may have its own system of planets, moons, and debris fields. The solar system is just one example of how such systems can form and evolve. As we zoom out further, the Sun becomes just one point of light among many. The planets become invisible. The distances between them disappear into the background. What once felt like a vast and complex system becomes a tiny structure within a much larger cosmic pattern. And yet, within this small system, everything necessary for life as we know it exists. Heat, light, chemical elements, and stable orbital conditions all combine to create a rare and fragile balance. The solar system is both ordinary in its structure and extraordinary in its outcome. As we conclude this chapter, we are left with a clearer understanding of scale. The solar system is not just a collection of planets orbiting a star. It is a vast, evolving environment shaped by forces that operate over billions of years and across distances that challenge imagination. It is the next step in our journey outward, but even now, it is only a small beginning in the larger structure of the universe. As we move deeper into our understanding of the solar system, we arrive at its most powerful and defining presence, the Sunday. Everything we have explored so far, from the smallest dust particles to the outermost planets, exists because of this single object. The Sun is not just another star in space. It is the central engine that shapes the structure, motion, and energy of the entire solar system. Without it, there would be no planets, no warmth, no light reaching Earth, and no conditions for life as we know it. Yet, even though it dominates our local space, the Sun itself is just one star among billions in the galaxy, which makes its true nature both familiar and deeply humbling. To understand the Sun, we must first let go of the way we think about it from Earth. From the surface of our planet, the Sun appears as a bright circle in the sky, rising in the east and setting in the west. It feels small enough to fit in our hand if we could reach out and touch it. This illusion comes from its enormous distance, about 150 million kilometers away, but distance hides its true scale. In reality, the Sun is a massive sphere with a diameter of about 1.39 million kilometers. To put this into perspective, more than 1 million Earths could fit inside the Sun if it were hollow. This comparison alone begins to break our sense of scale, showing how different the universe is from everyday experience. The Sun is composed mostly of hydrogen and helium, the two lightest and most abundant elements in the universe. At its core, however, conditions are extreme beyond imagination. Temperatures reach about 15 million degrees Celsius, and pressures are so intense that atoms are forced into continuous nuclear fusion. In this process, hydrogen nuclei collide and combine to form helium, releasing enormous amounts of energy. This energy is the source of sunlight, heat, and radiation that spreads throughout the solar system. Every second, the Sun converts millions of tons of mass into energy. a process governed by Einstein's famous equation that shows mass and energy are interchangeable. This energy does not reach the surface instantly. It begins in the core and slowly makes its way outward through dense layers of plasma. Photons created in the core are absorbed and re-emitted countless times as they move through the sun's interior. This journey can take thousands or even millions of years before the energy finally reaches the surface. Once it reaches the outer layer, known as the photosphere, it is released into space as light and heat. From there, it travels across the vacuum of space at the speed of light, reaching Earth in just over 8 minutes. This delay means that when we see the sun, we are always seeing a version of it from the past, not its exact current state. The sun's structure is divided into several layers, each with distinct properties. At the center is the core, where nuclear fusion takes place. Surrounding it is the radiative zone, where energy moves outward through radiation. Beyond that lies the convective zone, where hot plasma rises and cooler plasma sinks in a continuous cycle. Finally, there is the photosphere, the visible surface of the sun, followed by the chromosphere and the corona, which extend far into space. The corona is surprisingly hot compared to the surface, reaching temperatures of several million degrees, a phenomenon that scientists are still working to fully understand. From Earth, the sun appears stable and unchanging, but in reality, it is a dynamic and constantly active system. Its surface is covered with granules, which are convective cells of hot plasma rising and falling. It also contains sunspots, cooler regions caused by magnetic activity. These sunspots follow an approximately 1-1-year cycle, during which solar activity increases and decreases. During periods of high activity, the sun can produce solar flares and coronal mass ejections, which release bursts of energy and charged particles into space. When directed toward Earth, these events can affect satellites, communication systems, and even power grids. Despite its power, the sun is not eternal. It is currently in the middle of its life cycle, known as the main sequence phase. It has been shining for about 4.6 billion years, and is expected to continue for another 5 billion years before undergoing dramatic changes. Eventually, it will expand into a red giant, engulfing the inner planets, possibly including Earth. After shedding its outer layers, it will collapse into a white dwarf, slowly cooling over trillions of years. This life cycle shows that even the most powerful structures in the universe are temporary on cosmic timescales. The sun's gravity is the force that holds the entire solar system together. Every planet, moon, asteroid, and comet is in orbit because of this gravitational pull. These orbits are not straight paths, but curved trajectories shaped by the balance between gravity and motion. Each planet is constantly falling toward the sun, but because of its sideways velocity, it keeps missing it, resulting in an orbit. This delicate balance is what keeps the solar system stable over billions of years. Even the smallest changes in this balance can have significant effects. Comets from the outer solar system, for example, can be pulled inward when disturbed by gravitational interactions with planets or passing stars. These comets often follow highly elongated orbits, bringing them close to the sun before sending them back into the distant reaches of space. Their tails, made of gas and dust, form as they approach the sun and are heated by its radiation, creating some of the most spectacular sights in the night sky. The sun also emits a constant stream of charged particles known as the solar wind. This flow extends far beyond the orbit of Pluto, creating a vast bubble around the solar system called the heliosphere. Within this bubble, the sun's influence dominates the surrounding space. Beyond it lies interstellar space, where the winds of other stars begin to interact. The boundary of this region is not sharp but gradual, marking the edge of the sun's physical influence. One of the most important roles of the sun is its relationship with life on Earth. Nearly all energy used by living systems can be traced back to sunlight. Plants convert solar energy into chemical energy through photosynthesis, forming the base of the food chain. Fossil fuels are ancient stores of this same energy, preserved over millions of years. Even wind and weather patterns are driven by the uneven heating of Earth's surface by the sunday. In this way, the sun is not just a distant object in the sky, it is the source of nearly all energy that sustains life. Yet, despite its importance, the sun is not unique in the universe. It is a relatively ordinary star known as a yellow dwarf. There are stars much larger, hotter, and more luminous, as well as stars much smaller and cooler. Some stars live for only a few million years, while others can burn for trillions of years. The sun sits in the middle of this range, both in size and lifespan. This means that while it is essential to us, it is not exceptional in a cosmic sense. If we imagine moving away from the sun, the first thing we notice is how quickly its influence fades. Mercury, the closest planet, receives intense radiation, while Pluto, at the edge of the solar system, receives only a faint glow. By the time we reach the outer regions, sunlight is so weak that it resembles a bright star in the night sky of Earth. This dramatic decrease in energy with distance shows how dependent the solar system is on proximity to its star. The sun also plays a role in shaping space itself around it. Its magnetic field extends throughout the solar system, interacting with planetary magnetospheres and influencing cosmic particles. This magnetic environment is constantly changing, driven by the sun's internal activity. It creates auroras on Earth when charged particles interact with our atmosphere, producing glowing lights near the poles. These phenomena are visible reminders of the connection between Earth and the sunday. As we study the sun more deeply, we begin to see it not as a simple object, but as a complex, evolving system. It is both stable and changing, predictable and dynamic. It follows physical laws that we can measure, yet still contains mysteries that are not fully understood. Its surface roils with activity, its core burns with unimaginable energy, and its influence extends far beyond what we can directly see. At the same time, the sun is also a reference point for understanding everything else in the universe. Distances between stars, brightness of galaxies, and even the size of black holes are often compared to solar values. It becomes a unit of measure as well as a physical object. In this way, the sun is not only a part of the universe we observe, but also a tool we use to understand it. As we reach the end of this chapter, the sun stands as a powerful reminder of scale. It is enormous beyond human comprehension, Yet it is still just one star among hundreds of billions in our galaxy. It gives life to Earth, governs the motion of planets, and defines the structure of our local cosmic environment. But even with all its power, it is only a single point in a vast and expanding universe. As we leave the influence of the Sun behind, we enter a region that is almost impossible to describe using everyday experience. This is interstellar space, the vast and seemingly empty region that exists between stars. For most of human history, space was imagined as something relatively simple, a dark background where stars are placed like scattered lights. But the reality is far more complex and far more extreme. The space between stars is not simply empty. It is a thin, diffuse environment filled with particles, radiation, magnetic fields, and the remnants of ancient cosmic events. It is a place where distance becomes so large that even light, the fastest thing in the universe, struggles to cross it in reasonable time. To understand interstellar space, we must first realize what we are leaving behind. The solar system, with all its planets, moons, asteroids, and comets, is contained within a protective bubble created by the Sunday. This bubble is called the heliosphere, and it is formed by the continuous outward flow of solar wind. This wind pushes against the interstellar medium, creating a boundary where the Sun's influence begins to weaken. Crossing this boundary is not like crossing a line. It is a gradual transition where the Sun's particles become less dominant than the particles from other stars. The first spacecraft to enter this region was Voyager 1. Launched in 1977, it spent decades traveling outward through the solar system. It passed Jupiter and Saturn, then continued into the outer darkness beyond the known planets. After more than 35 years of travel, it crossed the heliopause, the boundary where the solar wind can no longer push outward against interstellar space. At that moment, it became the first human-made object to enter true interstellar space. Even though it is still within the Sun's gravitational influence, it is now surrounded primarily by material from other stars rather than our own. Interstellar space is not completely empty, but its density is extremely low. In some regions, there may be only a few atoms per cubic centimeter. To imagine this, consider that the air we breathe contains billions upon billions of molecules in the same volume. Compared to Earth's atmosphere, interstellar space is almost a perfect vacuum. Yet even in this emptiness, there is structure. There are clouds of gas and dust, shock waves from supernova explosions, and magnetic fields that stretch across light years. These interstellar clouds are not uniform. Some are cold and dense, forming regions where new stars are born. Others are hot and diffuse, shaped by the energy of nearby stars or the remnants of dying ones. Over time, these clouds collapse under gravity, forming new stellar systems. In this way, interstellar space is not just a void. It is a recycling ground for matter, where the remains of old stars become the building blocks of new ones. As we move farther from the Sun, the concept of distance begins to shift dramatically. Within the solar system, we measured space in kilometers and astronomical units. But in interstellar space, these units become meaningless. Instead, we use light years, the distance light travels in 1 year, which is about 9.46 trillion kilometers. Even this enormous number becomes necessary only because of how vast the space between stars truly is. The nearest star system to us is Alpha Centauri, located just over 4 light-years away. This distance may sound small in cosmic terms, but it is already unimaginably large. If the Sun were reduced to the size of a basketball and placed on Earth, the nearest star would be another basketball located thousands of kilometers away. Most of this space would be completely empty. Even traveling at the speed of light, it would take more than 4 years to reach it. With current spacecraft technology, the journey would take tens of thousands of years. Between the Sun and Alpha Centauri lies a region of space that is mostly invisible and undetectable to the human eye, yet it is not inactive. It contains faint traces of hydrogen gas, drifting particles of dust, and cosmic rays moving at nearly the speed of light. These cosmic rays are high-energy particles that originate from supernova explosions and other extreme cosmic events. They travel through interstellar space, sometimes for millions of years, before reaching planetary systems. One of the most important features of interstellar space is its connection to stellar life cycles. Stars are not permanent objects. They are born, live, and eventually die. When massive stars reach the end of their lives, they explode in supernovae, releasing enormous amounts of energy and scattering heavy elements into space. These elements, such as carbon, oxygen, and iron, are essential for forming planets and life. Without these explosive events, the universe would contain only simple elements like hydrogen and helium. Interstellar space is therefore not just empty space. It is the medium through which the building blocks of complexity are distributed. As we move deeper into this region, we begin to understand that space is not uniform. It has structure on enormous scales. There are regions where gas is compressed into dense clouds, forming the seeds of future stars. There are also vast bubbles created by supernova explosions where matter has been pushed outward, leaving behind low-density cavities. These structures can span hundreds of light-years, showing that even in emptiness there is organization. Magnetic fields also play a major role in shaping interstellar space. These fields are extremely weak compared to those on Earth, but they extend across enormous distances. They influence the movement of charged particles and help shape the formation of stars and galaxies. Although invisible, they are an essential part of the cosmic environment. As we continue outward, we begin to lose all familiar reference points. In the solar system, we could always relate distances to planets or the Sunday. In interstellar space, there are no such anchors. The nearest stars are separated by distances so large that light itself becomes a slow messenger. A signal sent from one star system to another takes years to arrive, meaning communication across even small cosmic distances is delayed and limited. This delay creates a fundamental separation between systems. Each star system becomes its own isolated island in a vast cosmic ocean. Even though the galaxy contains hundreds of billions of stars, the space between them ensures that interactions are rare on human timescales. Collisions between stars are extremely uncommon, and most systems evolve independently for billions of years. Yet, despite this isolation, the galaxy is not static. Stars orbit the center of the Milky Way, moving through space in complex patterns influenced by the combined gravity of all its mass. Our Sun takes about 225 million years to complete one orbit around the galactic center. This means that since the formation of the solar system, the Sun has only completed a small number of galactic orbits. The galaxy itself is constantly evolving, with spiral arms shifting and changing over time. In some regions of interstellar space, we find molecular clouds that are dense enough to block visible light. These dark regions appear as voids in the night sky, but in reality they are rich with material. Within them, gravity slowly pulls gas and dust together until new stars ignite. This process of star formation is ongoing throughout the galaxy, meaning that interstellar space is both a place of death and rebirth. As we move even farther from the Sun, we begin to see how radiation behaves across these distances. Light from distant stars takes years to reach us, meaning that when we observe them, we are looking into the past. A star 100 light-years away is seen as it was 100 years ago. This creates a natural time delay in our understanding of the universe. The farther we look, the deeper into the past we see. This concept becomes even more important when we consider galaxies beyond our own, but even within interstellar space. It already begins to shape our understanding of reality. Every point of light in the sky is a message from the past, traveling across vast distances of space and time before reaching us. Interstellar space also contains remnants of past events. Supernova shock waves ripple through space, compressing gas and triggering new star formation. These waves can travel for thousands of years across light-years of distance, influencing regions far from where they originated. In this way, the universe is deeply interconnected, even across enormous scales. As we approach the boundary between interstellar space and our solar system, we begin to understand how fragile our local environment truly is. The heliosphere protects us from much of the high-energy radiation present in interstellar space. Without it, Earth would be exposed to a much harsher environment. This protective bubble is constantly shaped by the balance between solar wind and interstellar pressure. At the edge of this bubble, the Sun's influence fades completely. Beyond this point, space is dominated by the conditions of the galaxy itself. This is the true beginning of interstellar space, where no single star holds control over the environment. As we conclude this chapter, we are left with a sense of scale that is difficult to fully grasp. The solar system, which once seemed vast, is now only a small region within a much larger structure. Interstellar space stretches between stars like an ocean of near emptiness, yet it is filled with the subtle traces of cosmic history. It is here that the universe reveals its true nature as both empty and full at the same time. A place where distance is not just a measure of space, but a measure of time, isolation, and connection across the galaxy. As we move beyond interstellar space, we begin to understand that individual stars are not scattered randomly in isolation. Instead, they belong to vast, structured systems bound together by gravity over scales that are almost impossible to comprehend. Our Sun is one of these stars, and together with hundreds of billions of others, it forms a single enormous structure known as the Milky Way galaxy. This is the true home of our solar system, not just space between stars, but a massive rotating system that defines the environment in which everything we know exists. At first glance, the night sky gives a simple impression. We see scattered points of light, each one a distant star. But what we are actually seeing is only a tiny fraction of what is really there. Many stars are too faint to be seen with the naked eye. Others are hidden behind clouds of gas and dust. When we look deeper using telescopes, the sky transforms completely. What appears as a simple scattering of lights becomes a vast structured system filled with patterns, clusters, and spiral shapes. This is the Milky Way galaxy as a whole system, not just individual stars, but a coordinated structure spanning unimaginable distances. The Milky Way is a barred spiral galaxy. This means it has a central bulge of stars, a flat rotating disk, and spiral arms that extend outward from the center. These arms are not solid structures. They are regions of higher density, where stars are more closely packed together. As stars orbit the center of the galaxy, they move in and out of these arms over time. The entire structure is about 100,000 light-years in diameter. To put this in perspective, light traveling at 300,000 kilometers per second would take 100,000 years to cross from one side of the galaxy to the other. Within this vast structure, our solar system is located in a relatively quiet region called the Orion Arm or Orion Spur. This is a minor spiral arm located between two larger arms of the galaxy. It is not the center, not the edge, but somewhere in between. Even so, this region contains billions of stars. Our Sun is just one of them, orbiting the galactic center at a distance of about 26,000 light-years. This orbit takes roughly 225 to 250 million years to complete. This period is sometimes called a galactic year. Since its formation, the Sun has completed only a small number of these galactic orbits. The center of the Milky Way is a very different environment from where we live. It is densely packed with stars, gas clouds, and extreme gravitational forces. At the very core lies a supermassive black hole known as Sagittarius A. This object has a mass about 4 million times greater than the Sun, yet it is confined to a region smaller than the orbit of Mercury. Around it, stars orbit at extremely high speeds, tracing paths shaped by intense gravity. This region is energetic, chaotic, and very different from the relatively calm environment of our solar system. The galaxy is not static. It rotates, but not like a solid object. Different parts of the galaxy rotate at different speeds. Stars closer to the center orbit faster than those farther out, but not in a simple linear way. This differential rotation helps maintain the spiral structure over long periods of time. However, the galaxy is also slowly evolving. Spiral arms shift, stars move through regions of higher and lower density, and gravitational interactions slowly reshape the structure over billions of years. Within the Milky Way, stars exist in many different environments. Some are isolated like our Sun, while others exist in dense clusters where thousands of stars are packed into relatively small regions of space. These clusters can be open clusters, which are loosely bound and gradually disperse over time, or globular clusters, which are tightly packed spherical groups of very old stars. Globular clusters orbit the galaxy like satellites, and some are nearly as old as the galaxy itself. The galaxy also contains vast clouds of gas and dust known as nebulae. These regions are the birthplaces of stars. Within them, gravity pulls material together until temperatures and pressures become high enough to ignite nuclear fusion. This process creates new stars, which then begin their long lives shining across the galaxy. At the same time, older stars are dying, releasing material back into space. This cycle of star birth and death is what drives the evolution of the galaxy over time. One of the most important realizations about the Milky Way is that it is not isolated. It is part of a larger group of galaxies known as the Local Group. This group contains more than 50 galaxies, including the Andromeda Galaxy, the Triangulum Galaxy, and many smaller dwarf galaxies. These galaxies are bound together by gravity and move through space as a connected system. The Andromeda Galaxy is the largest galaxy in the Local Group and is even larger than the Milky Way. It is located about 2.5 million light-years away from us. This distance is so large that the light we see from Andromeda today left the galaxy 2.5 million years ago, long before humans existed in their current form. In fact, every view we have of distant galaxies is a view into the past. The farther away we look, the older the universe appears. The Milky Way and Andromeda are also moving toward each other. In about 4 billion years, they are expected to collide and merge into a single larger galaxy. This process will not involve direct collisions between stars because the distances between them are so large. Instead, the galaxies will pass through each other, with their gravitational fields slowly reshaping both structures over time. Eventually, they will settle into a new combined galaxy, sometimes called Milkomeda by scientists. Beyond the Local Group lies even larger structures. Galaxies are not randomly scattered throughout the universe. They form clusters, superclusters, and vast filaments that stretch across hundreds of millions of light-years. Between these structures are enormous voids, regions with very few galaxies. This large-scale structure of the universe looks something like a cosmic web, with galaxies forming the threads and intersections of an immense three-dimensional network. The Milky Way itself is part of a larger structure known as the Virgo supercluster. This supercluster contains thousands of galaxies, all loosely bound by gravity. Even this, however, is not the largest known structure. On even larger scales, superclusters connect into filaments that stretch across the observable universe. These structures reveal that the universe is not uniform. It has patterns, clusters, and empty regions that together form a complex cosmic architecture. Despite its size, the Milky Way is still just one galaxy among perhaps 2 trillion galaxies in the observable universe. Each galaxy contains billions or even trillions of stars. Many of those stars likely have planets, and many of those planets could have conditions suitable for some form of chemistry or even life. This realization dramatically expands the possible scale of worlds beyond our own. Inside the Milky Way, the processes that shape stars and planets are continuous. Supernova explosions scatter heavy elements into space. These elements later become part of new stars, planets, and potentially life forms. Without previous generations of stars, there would be no carbon, oxygen, or iron. Every atom in our bodies was formed in the interior of a star or during a stellar explosion. In this sense, the galaxy is not just a collection of objects, it is a system that recycles matter across time. The movement of stars within the galaxy is also not random. Stars orbit the galactic center in stable paths, but they can also migrate over time. Gravitational interactions with spiral arms, molecular clouds, and other stars can slowly change their orbits. This means that the Sun may not always have been in the same region of the galaxy where it is now. It may have moved inward or outward over billions of years, carrying its planetary system along with it. The galaxy also contains dark matter, an invisible form of matter that does not emit light but has a strong gravitational effect. We know it exists because of how stars move within galaxies. Without dark matter, galaxies would not hold together as they do. The visible matter alone is not enough to explain their structure and rotation. Dark matter forms a large halo around galaxies, influencing their shape and behavior on the largest scales. As we continue to expand our perspective, the Milky Way begins to shrink in relative importance. What once seemed like the entire universe is now just one of many galaxies in a vast cosmic population. The Sun becomes a single star among hundreds of billions in one galaxy, which itself is just one of countless galaxies spread across space. Yet within this immense structure, there is still order. Gravity organizes matter into stars and galaxies. Energy flows from star to star, shaping the evolution of cosmic systems. Time stretches across billions of years, allowing complex structures to emerge from simple beginnings. As we reach the end of this chapter, the Milky Way stands as a bridge between the small and the infinite. It is large enough to contain billions of worlds, yet small enough to be just one component in a universe far larger than itself. It is our cosmic home, but not the limit of existence. Beyond it lies a universe filled with countless other galaxies, each with its own history, structure, and scale, waiting to be understood. As we move beyond the Milky Way, the sense of scale begins to change in a way that is no longer gradual but overwhelming. Up to this point, we have expanded our view from Earth to the Moon, from the solar system to interstellar space, and then to our home galaxy. Each step felt enormous in its own right, yet still connected to something familiar. But now, as we step outside the Milky Way, even the concept of a single galaxy begins to feel small. What lies ahead is not just a larger structure, but an entire network of galaxies stretching across distances so vast that they begin to reshape our understanding of reality itself. The first thing we realize is that the Milky Way is not alone. It is part of a small collection of galaxies bound together by gravity known as the local group. This group is not a dense cluster, but a loose gathering of galaxies moving through space together. It contains more than 50 known members, though most of them are small dwarf galaxies that orbit larger ones. At the center of this group are two dominant galaxies, our own Milky Way and a much larger spiral galaxy located nearby. These two systems define the structure and motion of the entire group. Even within the local group, distances are already difficult to comprehend. The space between major galaxies is measured in hundreds of thousands or even millions of light years. This means that light itself takes millions of years to travel from one galaxy to another. When we observe a neighboring galaxy, we are not seeing it as it is now, but as it was millions of years ago. This creates a natural separation not only in space, but also in time. Every galaxy we observe is a window into the past. The local group is not static. Its galaxies are moving through space under the influence of gravity. Some are orbiting larger galaxies, while others are moving along trajectories that will eventually lead to collisions. One of the most significant future events in our local region is the collision between the Milky Way and its nearest large neighbor. Although this sounds catastrophic, the vast distances between stars mean that direct collisions between individual stars are extremely unlikely. Instead, the galaxies will pass through each other, their shapes gradually distorted by gravitational forces. Over time, they will merge into a single, larger galaxy. This process will take billions of years, but it shows that even galaxies are not permanent structures. Beyond the local group lies a much larger structure known as the Virgo cluster. This cluster contains thousands of galaxies bound together by gravity. Unlike the loose structure of the local group, galaxy clusters are more densely packed and more dynamically active. Within these clusters, galaxies interact frequently. They can merge, strip material from one another, and trigger bursts of star formation through gravitational interactions. These environments are some of the most active regions in the universe. Galaxy clusters are not isolated either. They are part of even larger structures called superclusters. These superclusters contain multiple clusters of galaxies connected in a vast network. Our local group and the Virgo cluster are both part of a larger structure often referred to as the Virgo supercluster. This supercluster spans hundreds of millions of light years and contains thousands of galaxies grouped into clusters and groups. Yet even this is not the largest level of organization in the universe. As we expand our view further, we begin to see that the universe is organized like a vast cosmic web. This structure is made up of long filaments of galaxies, separated by enormous voids, where very few galaxies exist. The filaments are like threads connecting dense regions of matter, while the voids are vast empty spaces stretching across tens or even hundreds of millions of light years. This pattern is not random. It is the result of how matter distributed itself after the Big Bang, influenced by gravity and the expansion of space. In this cosmic web, galaxies are not evenly spread out. They are concentrated along filaments, forming chains and clusters. Where filaments intersect, we often find large galaxy clusters. These intersections are some of the most massive structures in the universe. Between them lie voids, regions so empty that they contain almost no galaxies at all. These voids are not completely empty, but compared to the dense filaments, they are vast regions of near-nothingness. The scale of these structures is difficult to express in familiar terms. A single filament can stretch for hundreds of millions of light years. A void can span even larger distances. If we were to compress the universe into a scale we could walk across, galaxies would be like tiny grains of sand arranged along invisible threads with enormous empty spaces between them. The universe, on its largest scales, resembles a web more than a cloud or a sphere. As we continue to observe deeper into space, we also observe deeper into time. Because light takes time to travel, distant galaxies appear as they were in the distant past. The farther we look, the younger the universe appears. This means that when we observe galaxies billions of light years away, we are seeing them not as they are today, but as they were billions of years ago, when the universe itself was much younger. In this way, space becomes a form of time machine, allowing us to look back into cosmic history. One of the most important discoveries about the large-scale structure of the universe is that it is expanding. Galaxies are not only moving through space, but space itself is stretching. This means that distances between distant galaxies are increasing over time. The farther away a galaxy is, the faster it appears to be moving away from us. This is not because galaxies are flying through space at high speeds in the traditional sense, but because the fabric of space itself is expanding. This expansion changes the way we think about distance. In a static universe, distances would remain constant, but in an expanding universe, distances grow over time. This means that the universe we observe today is different from the universe that will exist in the future. Galaxies that are currently visible may eventually move beyond our observable range, not because they disappear, but because the space between us and them becomes too large for their light to ever reach us. Despite this expansion, gravity still plays a strong role on smaller scales. Within galaxies and clusters, gravitational attraction is strong enough to hold structures together. This is why galaxies do not simply expand apart like distant points on a stretching surface. Instead, the expansion of the universe is most noticeable on the largest scales, where gravity is too weak to overcome it. Another important feature of large-scale cosmic structure is dark matter. Although invisible, dark matter makes up a large portion of the universe's total mass. It does not emit light or interact with electromagnetic radiation, but it exerts gravitational influence on visible matter. Without dark matter, galaxies would not be able to maintain their shapes, and the cosmic web itself would not form in the way we observe it. Dark matter acts like an invisible scaffold, shaping the distribution of galaxies across the universe. Alongside dark matter, there is also dark energy, a mysterious force responsible for the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy appears to push space apart. Its effects are most noticeable on the largest scales, where it drives galaxies away from each other at increasing speeds. The exact nature of dark energy is still unknown, but it plays a dominant role in the long-term evolution of the universe. As we move through these vast structures, we begin to realize that galaxies are not isolated islands. They are part of a continuous network shaped by both gravity and expansion. This network has evolved over billions of years, starting from tiny fluctuations in the early universe. Over time, these fluctuations grew into the complex structures we see today, guided by the laws of physics and the interplay between matter and energy. The cosmic web also reveals something profound about emptiness. What we call empty space is not truly nothing. Even in voids, there are traces of matter, radiation, and quantum fields. Space itself has structure and properties that influence how matter behaves. This means that the universe is not just a collection of objects floating in emptiness, it is a dynamic system where space, time, matter, and energy are deeply interconnected. As we expand our perspective further, the Milky Way and even the local group begin to shrink into insignificance. They become small components in a vast cosmic architecture that stretches far beyond anything we can directly observe in detail. Each galaxy is a tiny point in a much larger pattern, and each cluster is part of a network that spans the observable universe. And yet, despite this enormous scale, the universe follows consistent rules. Gravity, motion, and expansion operate across all levels, from individual stars to the largest cosmic structures. This consistency allows us to study the universe scientifically, even when its scale seems beyond comprehension. As we reach the end of this chapter, we find ourselves standing at a threshold. Behind us lies the familiar structure of our galaxy and local group. Ahead of us lies a universe organized not by isolated objects, but by an intricate cosmic web of galaxies, clusters, filaments, and voids. It is a universe that is both structured and expanding, both finite in age and vast beyond imagination. And still, even this enormous structure is only part of what exists within the observable universe, which is where our journey now continues. As we expand our view beyond galaxy clusters, superclusters, and the vast cosmic web, we reach a boundary that is not a physical wall, but a limit defined by light itself. This boundary is called the observable universe. It represents the region of space from which light has had enough time to reach us since the beginning of the universe. Beyond it, there may be more universe, more galaxies, more structures, but their light has not yet arrived. In a very real sense, the observable universe is not the entire universe, but only the part we can currently see. The idea of the observable universe is deeply connected to time. When we look into space, we are also looking back into the past. Light takes time to travel, and because of this, every object we observe is seen as it was when its light began its journey. The sun we see is 8 minutes old. The nearest stars are years old in our view. Distant galaxies are millions or billions of years old by the time we observe them. At the edge of the observable universe, we are seeing light that has traveled for nearly 13.8 billion years, arriving from a time when the universe was extremely young. The radius of the observable universe is about 46.5 billion light-years in every direction. This number is larger than the age of the universe in years because space itself has been expanding while the light traveled. This means that the objects we see at the farthest edges are now much farther away than when they emitted the light we are just now receiving. This expansion of space changes the way we understand distance entirely. It is not just a simple measure of separation, but a dynamic quantity that grows over time. Within this enormous volume of space lies everything we can currently observe. It contains hundreds of billions of galaxies, each with billions or trillions of stars. These galaxies are not evenly distributed, but form the same cosmic web structure we explored earlier, with filaments, clusters, and vast empty voids. On the largest scales, the universe appears surprisingly uniform. No matter where we look, the distribution of galaxies follows similar patterns. This observation is known as the cosmological principle, which states that the universe is homogeneous and isotropic on sufficiently large scales. However, this uniformity only appears when we zoom out far enough on smaller scales. The universe is highly structured. Stars form galaxies, galaxies form clusters, clusters form superclusters, and superclusters form filaments. But when averaged over billions of light years, these structures blend into a smooth cosmic background. This transition from complexity to uniformity is one of the most important features of the universe's large-scale structure. One of the most important pieces of evidence for understanding the observable universe comes from the cosmic microwave background radiation. This is a faint glow of radiation that fills the entire universe, visible in every direction. It is the oldest light we can observe, originating from a time about 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that light could not travel freely. Matter and radiation were tightly coupled in a dense plasma. As the universe expanded and cooled, atoms began to form, and light was finally able to move freely through space. That released light is what we now observe as the cosmic microwave background. This radiation is incredibly uniform, but it contains tiny fluctuations in temperature. These small variations represent the seeds of all future structure in the universe. Over billions of years, gravity amplified these tiny differences, leading to the formation of galaxies, stars, and planets. In a very real sense, every structure in the universe began as a small fluctuation in this ancient light. As we study the cosmic microwave background, we are essentially looking at a snapshot of the universe when it was in its infancy. It provides a direct link between the early universe and the large-scale structure we observe today. It also helps us determine key properties of the universe, such as its age, composition, and rate of expansion. The expansion of the universe is another fundamental aspect of the observable universe. This expansion was first observed through the redshift of distant galaxies. When we observe light from galaxies moving away from us, their light is stretched to longer wavelengths. This makes them appear redder than they would if they were stationary. The farther away a galaxy is, the greater its redshift, meaning the faster it is receding from us due to the expansion of space. This discovery led to the realization that the universe is not static. It is expanding in all directions. This expansion is not like an explosion from a single point into empty space. Instead, it is the expansion of space itself. Every region of space is stretching, causing galaxies to move away from each other on large scales. This means that from any galaxy in the universe, the same observation would be made. All distant galaxies appear to be moving away. giving the impression that each observer is at the center of expansion. As we look deeper into the observable universe, we also see that the farther we observe, the further back in time we are looking. This creates a natural limit to how far we can see. At a certain distance, we reach a point where the universe becomes opaque, not because there is anything blocking our view, but because we are looking back to a time before light could travel freely. This is why the cosmic microwave background appears as a spherical surface surrounding us. It is the edge of the visible universe in time, not space. Beyond this surface lies the unobservable universe, regions of space that exist but whose light has not yet reached us. These regions may contain galaxies, stars, and structures similar to those we see closer to us, but they are forever hidden from our current view. As time passes, the observable universe slowly expands, allowing light from more distant regions to eventually reach us. In this sense, the boundary of the observable universe is not fixed. It grows over time, but never fast enough to catch up with the most distant regions that are already receding faster than light due to cosmic expansion. Within the observable universe, galaxies are organized into a vast network shaped by gravity and dark matter. Dark matter forms the underlying structure, guiding the formation of galaxies and clusters. Although we cannot see it directly, its gravitational effects are essential for explaining how the universe is structured. Without dark matter, galaxies would not form in the way we observe, and the cosmic web would not exist in its current form. In addition to dark matter, the universe also contains dark energy, a mysterious force responsible for the accelerated expansion of space. Unlike matter and radiation, which slow down over time due to gravity, dark energy appears to increase the rate of expansion. This means that distant galaxies are not only moving away from us, but doing so at increasing speeds. Over extremely long timescales, this will lead to a universe where distant galaxies move beyond our observable horizon entirely. The observable universe also contains a huge range of cosmic environments. There are regions of intense star formation, where galaxies are actively producing new stars at high rates. There are also old, quiet regions where star formation has slowed or stopped. Some galaxies are spirals like the Milky Way, while others are elliptical, containing older stars and little gas. Some galaxies are irregular, shaped by collisions and gravitational interactions. This diversity shows that the universe is not uniform in appearance, even though it is statistically uniform on large scales. As we move toward the edge of the observable universe, we encounter the earliest galaxies ever formed. These galaxies are much smaller and less structured than modern ones. They are often irregular in shape and contain young, hot stars. Over time, these early galaxies merged and evolved into the larger structures we see today. By studying them, we can trace the history of cosmic evolution back to its earliest stages. One of the most profound aspects of the observable universe is that it has a horizon. This is not a physical barrier, but a limit set by the speed of light and the age of the universe. No signal, no matter how fast, can travel faster than light. This means there are regions of space that are permanently beyond our reach. Even if we waited forever, light from some parts of the universe would never reach us because space is expanding too quickly between us and those regions. This leads to a deeper realization. The universe we can observe is not necessarily the universe as a whole. It is only the portion that is connected to us through light and time. Beyond this region, there may be more universe, possibly even infinite in extent, but it is fundamentally inaccessible from our position. Despite this limitation, the observable universe is already unimaginably large. It contains more galaxies than there are grains of sand on Earth's beaches. Each galaxy contains billions or trillions of stars. Many of those stars likely have planets, and many of those planets may have conditions suitable for complex chemistry or even life. The sheer number of possibilities within the observable universe is staggering. As we conclude this chapter, we find ourselves at a strange intersection of knowledge and limitation. We can see farther than ever before in human history, yet we also understand that there are limits to what can be observed. The observable universe is both a window and a boundary. It shows us the vastness of cosmic structure, while also reminding us that there is more beyond what we can ever see. And even within this enormous visible region, the story is not finished, because the universe is still expanding, still evolving, and still revealing new layers of structure and mystery with every passing moment. As we continue our journey beyond the observable structures of galaxies and cosmic background light, we enter a deeper layer of understanding that is not just about space, but about time itself. Up to this point, we have explored distance on scales that stretch from planets to the edge of the observable universe. But now we begin to understand that the universe is not only expanding through space, it is also evolving through time. Every structure we see today is the result of billions of years of transformation, driven by the expansion of the universe and the passage of cosmic time. To understand cosmic expansion, we must first return to the beginning. The universe, as far as we can observe, began about 13.8 billion years ago in an extremely hot, dense state. This moment is commonly referred to as the Big Bang, although it was not an explosion in space, but rather an expansion of space itself. At the earliest moments, the universe was so hot and dense that familiar particles could not exist. Energy and matter were in a unified state, and the laws of physics as we know them were just beginning to take shape. As the universe expanded, it cooled. This cooling allowed energy to transform into particles such as protons, neutrons, and electrons. These particles eventually combined to form the first simple atoms, mostly hydrogen and helium. For a long time, the universe remained dark because light could not travel freely. It was filled with a dense fog of particles that scattered photons in all directions. This period is sometimes called the Cosmic Dark Age, not because nothing existed, but because light was trapped and could not travel across space. Eventually, as expansion continued, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. At this moment, light was finally able to move freely through space. This released light is what we now observe as the cosmic microwave background radiation. It marks the first moment in cosmic history where the universe became transparent. From that point onward, light could travel across space, carrying information about distant regions and early conditions of the universe. As time passed, gravity began to take effect on the slight irregularities in the distribution of matter. Some regions were slightly denser than others, and over millions of years these differences grew. Gravity pulled more and more matter into these dense regions, forming the first stars. These early stars were very different from the ones we see today. They were massive, short-lived, and composed almost entirely of hydrogen and helium. When they died, they exploded as supernovae, releasing heavier elements into space. These elements became the building blocks for later generations of stars and planets. Over billions of years, the universe transitioned from a simple state of hydrogen and helium into a complex environment filled with diverse elements, structures, and cosmic systems. This process is ongoing, meaning the universe today is very different from what it was in the past, and it will continue to change in the future. One of the most important discoveries about the universe is that it is expanding. This was first observed in the early 20th century, when astronomers noticed that distant galaxies were moving away from us. The light from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther away a galaxy is, the greater its redshift, indicating that it is moving away faster. This relationship shows that space itself is expanding uniformly. This expansion is not like objects moving through empty space. Instead, space itself is stretching. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they are moving across the surface, but because the surface itself is expanding. In the same way, galaxies are carried apart by the expansion of space. This expansion has profound consequences for the structure and future of the universe. It means that the universe was smaller in the past and will be larger in the future. If we reverse this expansion backward in time, we find that everything was once concentrated in a much smaller region. This leads to the conclusion that the universe has a finite age, approximately 13.8 billion years. However, expansion is not constant in speed. For much of cosmic history, gravity was slowing down the expansion due to the attraction of matter. But more recently, observations have shown that the expansion is actually accelerating. This means that distant galaxies are not only moving away from us, but doing so at increasing speeds. The cause of this acceleration is attributed to a mysterious component of the universe known as dark energy. Dark energy is not directly observed, but its effects are clear. It acts as a kind of repulsive force on cosmic scales, causing space itself to expand faster over time. While matter and gravity work to pull structures together, dark energy works in the opposite direction, pushing space apart. The balance between these forces determines the large-scale evolution of the universe. Because of this accelerated expansion, the future of the universe will look very different from its present state. Distant galaxies will eventually move beyond our observable horizon. Over extremely long timescales, only galaxies that are gravitationally bound to us will remain visible. The rest will fade from view, not because they disappear, but but because their light will no longer reach us. This leads to a concept known as cosmic isolation. In the distant future, galaxies that are not gravitationally bound will become invisible to each other. Each gravitationally bound system will effectively become its own isolated island in a vast, dark universe. Observers in those distant regions would see only their local group of galaxies, with no evidence of the larger cosmic structure that exists today. Cosmic expansion also affects the nature of time. Because light takes time to travel, observing distant objects is equivalent to looking back in time. The farther we look, the further into the past we see. This means that the universe acts like a layered structure of time, where different distances correspond to different epochs of cosmic history. At moderate distances, we see galaxies as they were billions of years ago, often younger and more active than nearby galaxies. At greater distances, we see the formation of the first galaxies. At the farthest observable distances, we see the universe in its earliest stages, shortly after the cosmic microwave background was released. In this way, the universe is not just a three-dimensional structure, but a four-dimensional one, where space and time are deeply connected. This connection between space and time is described by the concept of space-time. In space-time, events are not just located in space, but also in time. The expansion of the universe is therefore not just a change in spatial distances, but a change in the structure of space-time itself. This means that the universe is not a static stage where events occur, but a dynamic system where the stage itself evolves. As we study the large-scale structure of the universe, we see that it is shaped by both expansion and gravity. Gravity pulls matter together to form stars, galaxies, and clusters. Expansion stretches space between these structures, gradually increasing the distances between them. The interplay between these two forces creates the cosmic web we observe today. In the early universe, matter was distributed almost uniformly with only tiny fluctuations. Over time, gravity amplified these fluctuations, forming dense regions that became galaxies and clusters. At the same time, expansion stretched the space between these structures, preventing everything from collapsing into a single point. This balance allowed complexity to emerge while preserving large-scale structure. Another important aspect of deep cosmic time is the life cycle of stars. Stars are not eternal. They are born from clouds of gas, live for millions to trillions of years depending on their mass, and eventually die. When they die, they return their material to space, enriching it with heavier elements. This cycle of birth, evolution, and death has been ongoing for most of the universe's history. As a result, the universe today is chemically richer than it was in the past. Early stars contained almost no heavy elements, while later generations contain a wide variety of elements necessary for planets and life. This means that the universe is not only expanding in space, but also evolving in complexity over time. Looking far into the future, cosmic expansion suggests that the universe will continue to grow more isolated and colder. Star formation will eventually slow as gas becomes depleted. Existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. over extremely long timescales, even these remnants will fade, leading to a universe dominated by darkness and thin radiation. This long-term future is sometimes called the heat death of the universe, a state where all usable energy is evenly distributed and no further large-scale processes can occur. While this scenario lies trillions or even far more years into the future, it is a direct consequence of the current understanding of cosmic expansion and thermodynamics. Despite this distant fate, the present universe is full of activity. Galaxies collide and merge, stars are born and die. Black holes grow and shape their environments. Planets form and evolve. Life, at least in one known location, has emerged as part of this cosmic process. All of this happens within a universe that is still expanding and still changing. As we conclude this chapter, we realize that cosmic expansion is not just a feature of space, but a fundamental aspect of existence itself. It connects the earliest moments of the universe to its distant future. It shapes the distribution of galaxies, the flow of time, and the ultimate fate of all structures. It turns the universe into a dynamic system where nothing remains fixed forever. And yet, even as the universe expands and evolves, it remains governed by consistent laws. These laws allow us to understand its history, measure its present, and predict its future. In the next stage of our journey, we move toward the ultimate boundary of understanding, where the known universe meets the unknown, and where questions begin to outnumber answers. As we reach the final stage of our journey through scale, we arrive at a place where measurement itself begins to lose meaning. Every step we have taken so far has been an expansion outward, from Earth to the Moon, from the solar system to the galaxy, from galaxy clusters to the observable universe. Each layer revealed a larger structure, a deeper time scale, and a broader system of physical laws. But now we reach a point where the universe confronts us with its most profound characteristic. It is not just large, it may be unbounded, and even if it has limits, those limits are not accessible to us in any direct way. This is the boundary where science meets uncertainty, and where known physics begins to stretch toward the unknown. At the edge of the observable universe, we are already facing a fundamental limit. We can only observe so far because light has only had a finite amount of time to reach us since the beginning of the universe. Beyond this horizon lies more universe, but it is forever hidden from direct observation. This is not because it does not exist, but because its light has not had enough time, or may never have enough time, to reach us due to the expansion of space. In a very real sense, the universe we can see is only a portion of the total universe. What lies beyond is unknown, not necessarily non-existent. This idea forces us to confront a deeper question. Is the universe finite or infinite in size? Current observations suggest that space is extremely close to flat on large scales. A flat universe can be infinite, meaning it may extend without end in all directions. However, it could also be finite but unbounded, like the surface of a sphere, but in higher dimensions. In such a case, traveling far enough in one direction might eventually bring you back to your starting point, though on scales so vast that it would take longer than the age of the universe to complete the journey. At present, we do not know which possibility is correct. What we do know is that the observable universe represents only a small fraction of what may exist. If the universe is infinite, then the observable region is just a tiny bubble within an endless expanse. If it is finite but much larger than what we can see, then the observable universe is still only a local patch of a much greater structure. In either case, what we can observe is fundamentally limited by the speed of light and the age of the cosmos. As we move beyond observational boundaries, we also encounter the limits of physical theory. Our understanding of the universe is based on well-tested laws of physics, including general relativity and quantum mechanics. These theories describe the behavior of matter, energy, space, and time with extraordinary accuracy. They allow us to predict the motion of planets, the structure of galaxies, and the evolution of the universe itself. However, there are regions where these theories begin to break down, particularly at the very beginning of the universe and at the centers of black holes. At the earliest moments after the Big Bang, the universe was in a state of extreme density and temperature. In this regime, the known laws of physics are not sufficient to fully describe reality. We can trace the evolution of the universe back to a fraction of a second after its beginning, but before that point, we need a theory that unifies gravity and quantum mechanics. Such a theory, often called quantum gravity, does not yet exist in a complete and experimentally verified form. This means that the very origin of the universe remains partially hidden behind a theoretical boundary. Similarly, inside black holes, gravity becomes so strong that it curves space-time to extreme levels. At the center of a black hole lies a region called a singularity, where density is thought to become infinite according to classical equations. However, this infinity is widely believed to indicate a breakdown of our current understanding rather than a physical reality. A complete theory of quantum gravity would likely replace this singularity with a more accurate description. But until such a theory is developed, the true nature of these regions remains unknown. These limits highlight an important truth about our understanding of the universe. Our knowledge is powerful, but it is not complete. There are boundaries beyond which our current models cannot reliably describe reality. These boundaries are not just spatial or temporal, but conceptual. They represent the edges of human understanding at this stage of scientific development. Beyond these theoretical limits, we enter a more philosophical region of thought. If the universe is infinite, then every possible configuration of matter may occur somewhere. This leads to the idea that there could be regions of space so far away that they contain galaxies, stars, and even planetary systems almost identical to our own. While this idea is speculative, it arises naturally from certain interpretations of cosmological models. However, these regions would be so far away that they are forever inaccessible, even in principle. Even within the observable universe, there are structures so large that they challenge our sense of scale. Filaments of galaxies stretch across hundreds of millions of light-years. Superclusters contain thousands of galaxies bound together by gravity. Voids span even larger distances, creating enormous empty regions that dwarf the structures around them. Yet even these vast formations are small compared to the full extent of what may exist beyond observation. As we reflect on this, we realize that scale in the universe is not linear. It does not simply increase in a straightforward way. Instead, it unfolds in layers, each revealing a new level of structure and complexity, from planets to stars, from stars to galaxies, from galaxies to clusters, from clusters to the cosmic web, and from the cosmic web to the observable universe. Each step expands both space and time in ways that challenge intuition. But at the final level, we encounter something different. We encounter not just larger structures, but the limits of structure itself. Beyond the observable universe, we cannot confirm what exists. Beyond the earliest moments of cosmic history, we cannot fully describe what happened. Beyond black hole interiors, we cannot currently predict what lies within. These are not gaps in imagination, but boundaries in physical knowledge. And yet, even within these boundaries, the universe remains deeply ordered. The same physical laws that govern a falling object on Earth also govern the motion of galaxies across billions of light years. The same forces that shape atoms also shape stars. This consistency suggests that even the unknown regions of the universe are likely governed by principles that are continuous with what we already understand, even if we have not yet fully discovered them. There is also a deeper realization that comes from studying the universe at this scale. Everything we observe, from the smallest particles to the largest cosmic structures, is connected through time. The light we see from distant galaxies tells us about the past. The cosmic microwave background reveals the early universe. The chemical elements in our bodies were formed in ancient stars. In a very real sense, we are not separate from the universe we observe. We are part of its ongoing evolution. This connection leads to one of the most profound insights of modern cosmology. The universe is not just something we observe from the outside. We exist within it as active participants in its history. Every atom in our bodies, every photon that reaches our eyes, every structure we build, and every thought we form is part of the same cosmic story that began billions of years ago. As we reach the final boundary of this journey, we are left with both knowledge and mystery. We understand more about the universe than at any previous point in human history. We can describe its structure, its evolution, and its large-scale behavior with remarkable precision. And yet, we also recognize how much remains unknown. The universe may be infinite or finite, fully observable or partially hidden, completely understood in principle, or forever beyond full comprehension. What lies beyond the known universe is not just a physical question, but a reminder of the limits of observation itself. No matter how powerful our instruments become, there will always be horizons defined by light, time, and the expansion of space. These horizons are not failures of science, but fundamental features of reality. And so, at the edge of everything we can observe, we find not an ending, but a perspective, a reminder that the universe is far larger, older, and more complex than any single viewpoint can capture. It stretches beyond galaxies, beyond clusters, beyond the cosmic web, and beyond even the limits of observable space and time. This is the true scale of the universe, not just vast in distance, but layered in time, structure, and possibility. And even now, as we stand at the boundary of what we can know, the universe continues to expand, evolve, and reveal new questions that may shape the next chapter of understanding yet to come.